mass enclosed within the shell. So we were kind of doing this to compute the central pressure a bit ago. And dm is 4 pi r squared rho bar dr. That's the mass of the shell itself. Thus the potential energy of the shell can be written in the form of du equal to minus 3g all brackets 4 pi rho bar over 3 squared r to the 4 dr. So there's some relation basically with all of the gravitation stuff and this potential energy. The potential energy of a planet with radius r is obtained by integrating over all the shells from r equal to 0 to r equal to big R, which is the big radius of the planet. So you basically get U, which is the potential energy now, because we know what du is because of that shell. Now we're going to integrate over all the shells, and eventually we get minus 3 over 5 big G m squared over r. By decreasing the radius r of the planet while keeping its mass constant, because you could, we can decrease the gravitational potential energy, U, by du dt. So now we're taking a derivative of this potential energy with respect to time as a function of time. Then you get basically m would be constant. The big R is constant, but maybe the part that you're changing with time, that part can be taken, you could take a derivative of that. So you would get 3/5 gm squared over r squared comes out, and then dr dt. So basically we're trying to solve for the contraction rate of the planet. We know the mass, the radius, we can take integrals to get the potential energy, and then ultimately we want how this potential energy is changing. So solving for the contraction rate of the planet, we find that dr dt as a, now dr dt is on the left hand side, we get 5/3 du dt r squared over gm squared. If Jupiter's excess radiation, so it's almost like we do all this math and then we compare Jupiter with the other planets, knowing that its mass is so much different than the others. So if Jupiter's excess radiation is around 4 times 10 to the 17 watts, comes from gravitational potential energy, then Jupiter must be contracting at the rate of, plugging it all in, around minus 1.6 times 10 to the negative 11 meters per second, which is around minus 500 kilometers per gigayear. So let me say that again. So it's minus, because it's a contraction, 1.6 times 10 to the negative 11 meters per second, or minus 500 kilometers per gigayear. Because the meters per second is it's a very small number in meters per second. So if you consider it in kilometers per gigayear, then it's a little bit better. So during the lifetime of the solar system, which is around 4.6 gigayears, Jupiter need only have contracted by around delta R of around 2,300 kilometers. So not a whole lot. Basically, this contraction could have happened because basically 4.6 gigayears, we're only 4.6 gigayears old. So Jupiter need only have contracted around 2,300 kilometers, about 3% of its current radius, in order to maintain radiation at its current rate. So it's such an interesting thing because it's so huge and it could be contracting, releasing this potential energy. You get this radiation. Depending on its radiation, we're like, okay, let's do the math. What kind of contraction could it have done? And it's not like a very shocking level of contraction. Basically, over the course of our entire lifetime of this solar system of 4.6 gigayears, it could have contracted around 2,300 kilometers, which is nothing for the delta R, that is, which is nothing for Jupiter. And it would have maintained its